My dear students, I welcome all of you for today's session on design and analysis of algorithms. In this session, let me discuss about some more important problem types. In previous session, I have discussed about three problem types which we used to come across in our day-to-day life, which you're already familiar with. Those problem types which you have discussed in previous sessions were one on sorting, the other on searching, and the third, what we have discussed in last session, was on string processing. Clear? So in this session, we will have look at further problem types. Okay. In your previous semester, you studied discrete mathematical structures, right? The part of that subject was on graph theory. It was very important part, graph theory. Think all of you remember about graph theory. Means the concepts of graph theory. Clear? What and all were in your syllabus in previous semester. Got it? So now we'll look at those graph problems and graphs. Clear? So and we'll have a look at some combinatorial problems. And I mean to say, in your previous semester, I taught you about the permutation combination. Hope you remember. Okay, permutations or combination, what actually they are. So a combination means selection. Permutation means some arrangement, right? So this problems belong. We can design an algorithm. Okay, we can design an algorithm to solve problems on permutations and combinations also. And such problems we call combinatorial problems. Then we will have a look at the algorithms on geometry. In your mathematics, you heard about geometry, right? Okay. Geometric way of algorithms for to solve geometric problems. Okay. And this will have a look at two types of problems. One is convex hull problem. Okay. And concave problem. We'll have a look at those two. Clear? So then we'll have even a look at some numerical problems. Okay. So now coming to agenda of this session. Okay. First, we'll have a look at graph problems. So before that, I think you're familiar with graph theory. Clear? If not, go through your graph theory again and have a refresher course on that. Review your graph theory. Got it? Because that's the base for graph problems. Next, combinatorial problems. Again, you studied in your previous academic semester. The same knowledge you should have here in order to design an algorithm to solve problems of permutations, combinations. Clear? Then we'll have a look at geometric problems. At the last, we'll have a look at numerical problems. Now, first we will see what actually graph problems. So before I say graph problems, you need to know what actually graph is, right? So don't think graph. I think what I think you might be wondering, you might be thinking graph as something you have used in physics lab or chemistry lab, right? To plot something on XY. Some graph sheet will be there. You need to mark some points over x-axis and you need to point some points over y-axis. Then you need to draw a curve. Of course, that's a graph. But here, in this context, we are dealing with not a two-dimensional graph. We are dealing even with a three-dimensional graph. Okay. Of course, what I studied in physics lab as well as chemistry lab, plotting that's a graph. Okay. But here we'll have a precise definition of graph. Okay. We'll have a clear definition of graph. What actually graph is that? And what are the applications of graph? We'll have a look and we'll have a look at some graph problems. Okay. So now coming to graph, okay, let me tell you. So before I tell you about this graph, now I'll show you next slide, one pic. Just have a look at this. So something you're seeing right here, just have a careful look at this slide, okay? In this slide, I've drawn one shape. I mean, I've drawn on picture. Okay, and this picture there are three vertices we call A, B, C, D. Clear? And among these vertices, okay, few vertices are some pair of vertices are connected. Clear? I repeat. Have a look at this slide. In this slide, I've drawn one pick. Let me call it a pick. Got it? In this pick, there are four vertices: A, B, C, D. Or let me call, even I in some context I will call them as a node. Got it? A, B, C, D or vertices are also called as nodes. Just among these vertices, okay, a pair of vertices have been connected. Is it? For example, let me say a pair A and B are connected. Similarly, a pair A and C are connected. A pair C and D are connected. A pair C and B are connected. D and B also connected. Got it? Means the pair that have been connected through a line, okay, what we call through a line, right? That we call an edge. Now, such things we call a graph. Clear? I repeat, you had a clear look at the slide, right? You had a clear observation on the pic, what was there on the slide, right? So that pic I'll call as a graph. Now, let me tell you definition of graph. What actually graph? Graph is nothing but a collection of vertices such as A, B, C, D. To be more precise, what I call graph is nothing but a collection of, okay, finite. Finite means countable, because ABCD, I need to count. I can say there's a four vertices. Non-empty. Non-empty means it's not empty. Non-empty set of vertices. I repeat, see, graph is nothing but a finite, non-empty set of vertices. Got it? And a set of edges. See here, what I said, a graph is a finite, non-empty set of vertices and a set of edges. See, for a set of vertices, I said non-empty. Remember, for a set of vertices, I said non-empty. But for set of edges, I didn't say anything empty or non-empty. Clear? For set of edges, I won't call empty or non-empty. I didn't say empty or non-empty. So I repeat, graph is nothing but a finite, non-empty set of vertices and a set of edges. So what this definition says means, this definition says that in order to call some pic as a graph, okay, in order to call a pic as a graph, that pic should have at least one vertex. Remember, a pic should, in order to call that pic as a graph, that pic should have at least one vertex. And edges may be at least one vertex. Means exactly if one vertex is also there, I can call it as a graph. A graph need not have an edges. Got it? Clear with this? A graph is a finite, non-empty set of vertices. I mean, there should be at least a one vertex. Got it? Or exactly one vertex. Need not have an edges. But edges can be there, but edges may not be there also. Got it? So then we call such a pic as a graph. Clear with this? So in this graph, what I said, non-empty finite set of vertices. Of course, because there are four vertices. A set of edges, of course, there are 1, 2, 3, 4, 5, 6 edges. But even let me tell you, only if I add this vertices, okay, A, B, C, D, and if the edges were not there, I repeat, if in this peak assume there was only this vertices A, B, C, D, but none of the edges, even then I'll call that as a graph. Got it? When clear, got it? Mean all those vertices A, B, C, D, I call an isolated vertices. isolation. You have what nowadays you're familiar with isolation, right? Isolated means separated. Got it? So in this graph, suppose A, B, C, D, among A, B, C, D, if there were no edges, means there no connection between any of these vertices. We call those vertices are isolated, but we call them as a graph. Clear with this? So now we'll come to graph. Once again, we'll say, got it? See here, a graph is a collection of points called vertices, some of which are connected by line segments called edges. Clear with this, right? I said. Now, what are the applications of graphs? What are the applications of graphs? Graphs are used for modeling a wide variety of real-life applications, including transportation and communication networks, project scheduling, and games. Let me tell you one example, okay? Suppose now what you or your friends together are going to plan a trip, 1 or 2 days trip, or let me say 3 days trip. Got it? So now you will you want to start with your source location. Let me say you want to start with source location, let it be Kushalnagar. Okay. Now, what you want to cover the other places of our state. Got it? So then you need to come back to source. That is Kushalnagar. Means you want to plan a trip starting from Kushalnagar. Okay, you want to cover all other districts of our state, Karnataka, and you need to come back to Kushalnagar. So, how means when I plan a trip such that I need to cover all the places, all the districts, tourist spots. Okay, but with optimum distance. But I mean to say minimum distance I need to plan. Minimum distance I need to make use to cover all the places. So, what now? How to plan this? Okay, because we know that the adjacent districts, okay, adjacent cities, okay. So first, what we need to represent? I mean to say, what we can say, we can represent all those cities or districts as vertices. Got it? You will represent all districts, all tourist spots as vertex. And the highway that connects, the road that connects, got it, those tourist spots or districts is nothing but an edge. We will represent as an edge. I repeat, the place as tourist spots, districts will represent as a vertex, and the highway that connects those district will represent as what, an edge. Got it? And between each pair of district, we know what may be the distance in terms of kilometer. Okay, that will represent like a number on this edge. Got it? Suppose A, B, C, D represents some tourist spots. Okay, the edge line that connects A and B represents an highway that it connects two cities A and B, and the 2 represents the distance to travel from A to B. Got it? So, I mean, this example I tell you. So, okay, let me clear you with this transportation problem. Now, what I said, I need to travel entire places A, B, C, D. Let me say, I'm starting from source A. I want to cover all the places A, B, C, D. Sorry, I want to start from A. I need to cover all other places B, C, D, and I need to come back to A. Okay. So what I said, with minimum distance, I need to cover my tour. So when I give this problem, okay, with all inputs to you guys, everyone will come up with their solution. So one might say, sir, I will start from A. I'll first cover B, then I'll visit C, then I'll visit D, then I'll come back to A. So it will take 18 units of distance. The other guy will say, sir, I'll start with A, then starting with A, I'll visit B, then D, then C, then A. it takes 11 units of distance. The other guy will say, sir, starting from A, I'll visit first C, then B, then D, then I'll come to back to A. This will take 23 units. So each will come up with the solution, right? So, but which solution is the best? The solution I call best is the one that covers all the places with minimum distance. So look at the among the solutions I've listed below the graph. Okay, the second and the fourth solutions are optimal. Got it? So starting from A, you visit either B or C. If you visit B, you visit next D. If you visit C, you visit next D. I mean to say, we can have any number of solutions, but we need to choose the optimum one. So this is one application of graph. I think clear with this graph? Got it? So real life applications. So in general, what is graph? Finite set of vertices, some of which connected by an edge. Line we call an edge. Okay. So now coming to application, I said modeling real life applications such as transportation, communication networks, project scheduling, games. Next, estimation of the web's diameter. The maximum number of links need to follow to reach one web page from another by the most direct route between them. Clear? So now clear with the graph, and it's one of the application what I said, transportation, tour, planning a tour. Got it? So now there are some graph problems. Okay, there are usually more than three, but I listed three graph problems. The first graph problem, what I'm saying is graph traversal algorithm. See here, graph traversal algorithm. Name what it says, traversal. Traversal means, I mean to say, okay. Now let me say, you can let me say, see, listen. When starting from any city, can I visit all other cities through the road? If yes, how to visit all other cities starting from any city? You see, traversing the graph. I mean, if I represent my entire state as a graph, entire state I represent as a graph. Okay, starting from any source node, source city, what are the ways of traversing all other cities? Got it? That is graph traversal algorithm. Got it? So how to visit all the points in a network? Now, starting from any source city, how I can visit all other cities in a state when I represent state as a graph. Okay. Next, shortest path algorithm. So what is the advantage of shortest path algorithm? Let me tell you. See here, now I said I can represent the entire state, clear, as a graph. I mean the districts as a nodes of vertices, the highway that connects two cities, two districts as an edge. Clear? So let me tell you an example. Suppose from Kushal Nagar, I need to travel to Bangalore. Okay. So what are the possible routes I have? One thing, from Kushal Nagar, I can go to Piriyapatna, Unsur, Mysore, then to Bangalore. Clear? If not, the other route is there. Starting from Kushal Nagar, let me go to Konanuru, okay, Valenarsipura, clear, Kunigal, Nelmangla, then to Bangalore. Means between a pair of any cities, between any pair of any, okay, between a pair of any two nodes or between a pair of any two cities, there may be any number of routes are possible. Clear? So which route is the best? Okay, so which route is the best? To decide that, I will prefer graph. So I will represent the entire state as a graph. Got it? Entire my state Karnataka as a graph. Okay, then I will identify the number of possible paths between any two pair of cities. Okay, then I'll compute the distance between those two pair of cities through those paths. I'll identify all possible paths between a pair of cities. Got it? Then I'll compute the distance between the pair of those two cities among those paths, and I'll choose the one with the shortest distance. So the next advantage of graph problem is to identify shortest path algorithm. Okay, let me tell you one thing, one example into graph traversal algorithm. What I said, how to visit all the points in a network, right? So the advantage of this, the first algorithm is that we can see whether any city is not reachable through an highway. Got it? For example, let me say, rather than representing straight as a graph, got it? Straight as a graph, okay? Let me represent nations. To be more clear, okay, let me tell you, in general, I will tell you, okay? Now, from Kushal Nagar, I can go up to Kanyakumari, right? I can traverse up to Kanyakumari border, okay? I can traverse. But to travel to Sri Lanka, can I travel through the road? I need to travel through the ship. Got it? So means that we call an isolated. It's not reachable one. Clear? Sri Lanka, we call it's unreachable through by road. Got it? We need to traverse through ship. Clear with this? So graph traversal algorithm identifies the any node which is not reachable. For example, let me say in this graph, assume there was one more vertex, say E, somewhere on the paper, okay, and the T is not connected to any of the vertices A, B, C, D. Got it? Assume there is one more node E, and the T is not connected to any of the vertices A, B, C, D. Got it? Now, from A, I can traverse through A to any of the cities B, C, D, but I can't traverse E. Is it? Because E is not connected to any of the cities. So graph traversal algorithm is also used to identify is there any node or vertex, any city which is not reachable. Next, topological sorting for digraphs. It's very important. Okay, interesting problem. We'll have in detail. Okay, and for the session. So at present, I'll tell you in brief. So let me tell you, topological sorting, what it says, it's a set of courses with the prerequisites consistent. Means topological sorting, it tells you what you need to learn before you proceed to any other subject. Okay. Without prerequisite, you can't move to any subject, right? I mean, let me tell you. Now you're studying this algorithm, right? So when I say you are going to study an algorithm, can you start your first? Can I teach you an algorithm in your first semester itself? No, because you need to have a prerequisite to study algorithm. What the prerequisite? One is discrete mathematical structure. So before you choose design and analysis of algorithm, you should have learned the course discrete mathematical structures. You should have learned graph theory. You should have learned data structures. So topological sorting, it tells which course you need to learn first, which course you need to learn next. So this is about topological sorting. So set of courses with the prerequisites consistent. So this is about graph problems. Okay, traveling, there are two important problems. Okay, traveling salesman problem. Okay, traveling salesman problem is nothing but this problem. Means I'm planning a tour. I am planning a tour. I want to start from A. I need to cover all other three cities and return back to A. What is the shortest tour? This is a traveling salesperson problem. Got it? So traveling salesperson problem is the problem of finding the shortest tour through n cities that visit every city exactly once. Okay, one more thing I need to tell you. So you have while traversing from A, B, C, D. Okay, you should visit each city exactly once. See, when I plan a trip now, I will plan from source to one city, then to other city. Then to move to the other next city, I should not visit the other already visited city. This is the constraint. Okay, so traveling salesperson problem we call TSP is the problem of finding the shortest tour through N cities that visit every city exactly once. Okay. Now the graph coloring problem. Graph coloring problem asks you to assign the smallest number of colors to vertices. Smallest number of colors to be assigned to vertices so that no two adjacent vertices are of the same color. So now let me tell you. I mean, here there are four vertices, right? A, B, C, D. Now I haven't colored any of the vertices here. But graph coloring problem, what it says, what should be the minimum number of colors? What should be the minimum number of colors so that you can color A, B, C, D? So that none of the adjacent. For example, if I say A, it's adjacent of B because it is connected directly to A. Even its adjacent is D. D is an adjacent to A because even it is directly connected to A. Now I say C is also adjacent to A. Got it? I mean to say, graph coloring problem is what is the minimum number of colors you should choose to color A, B, C, D, so that no two vertices, two adjacent vertices, okay? No two adjacent vertices should be of the same color. Suppose if I choose red to A, then B should not be colored with red, D should not be colored with red, C should also not be colored with red. Clear? So this is graph coloring problem. Okay, now combinatorial problem. Again, combinatorial means the possible with the same example I tell you. So combinatorial problem means I told it is dealing on permutation combinations. Clear? Got it. Now combinations, selections. Got it. So the best example here, it's a traveling salesperson problem and graph coloring problem. I'll make you to easily understand the combinatorial problem through TSP, traveling salesperson problem. See here, the main objective of combinatorial problem is optimization. The main objective of combinatorial problem is optimization. Optimization means okay. The main objective of combinatorial problem is optimization. Means in case of profit I should yield maximum. In case of loss, I should risk with minimum. Okay. So now TSP will come to this. We'll come back to TSP problem. So here, as a combinatorial problem is here the problem is you plan a trip from A, visit all other cities B, C, D exactly once. Come back to A. Got it? This is the problem given to you. So next, while the conditions that you start from A, visit all other cities exactly once, come back to A. But the goal here is optimization, means minimum distance. So there are a lot of combinations possible here. Either A, B, C, D, A, A, B, D, C, A, A, C, B, D, A, A, C, D, B, A. There are a lot of combinations I have obtained. Among this combination, I need to choose one with the minimum distance. That is an optimization. So got it. This traveling salesperson problem is an example for optimization. Got it? So next, graph coloring problem, even to it's an example for combinatorial problem. So the main drawback is that combinatorial problems are the most difficult problems in computing. Okay. Why I'll tell, because I discussed about orders of growth, you remember, right? The best is logarithmic, then n log n, quadratic, cubic. The worst are exponential and factorial, right? Exponential and factorial. Got it? So what actually happens now, these combinatorial problems will belong to last two cases usually. Okay. It will be exponential. Got it? So we call the most difficult problems in computing. For example, let me tell you. Here, TSP is a combinatorial problem. I have given you how many cities? 4 cities. For this 4 cities, how many combinations? 6 combinations. So I need to find all 6 combinations, 6 permutations of whatever it be. Okay. So if number of cities increases, the length of the combinations also increases. Got it? So we call it's a worst difficult problems. For example, let me say subset problem is there. Okay. There's some subset, you know, right? If in a set, if there are n elements, how many subsets are possible? In a set with n elements, how many subsets are possible? We know 2 power n subsets. I mean, you need to identify one particular subset means you need to list all possible subsets, 2 power n subsets. You need to list all 2 power n possible subsets. And you need to locate the one desired to your solution, your objective. I mean, in subset problem, a set contains n elements, 2 power n subsets are possible. You need to list all 2 power n subsets. After listing all 2 power n subsets, you need to locate that which meets an objective, whether to maximize or minimize. So subset problem is also combinatorial problem. It's an exponential in worst case. So see here, I said, right, not only permutation, combination, a subset, got it, is also a combinatorial problem. So now geometric problem, okay. So deals with it's like geometric objects, okay. We have studied in means deals with points, lines, triangles, circles, polygons, so and so. Means I need to design an algorithms on just geometrical shapes. Okay, there are 2 problems, very important. The closest pair problem, the convex hull problem. Okay, we will have in detail about this. One second. So in geometry, we are dealing with the problems on points, lines, triangles, circles, polygons. There are 2 types of problems. One is closest pair and convex hull. I mean, on an XY plane, there may be any number of points. Okay, assume there are some n number of points. Among those n number of points, you need to identify those 2 points which are close to each other. Got it? N number of points distributed randomly on a plane. Identify 2 points which are close to each other. That is closest pair problem. Okay. Yeah. So next, we'll have a look at numerical problems. So numerical problems means we have in your CCP itself, we have solved quadratic equation, right? Clear? So next, there are some problem like square root. Okay, to determine the square root. how to determine square root of any number. Got it? Such problems who might come or to determine a number is a prime or not, numerical problems, okay, evaluating some sign functions, okay, you know, sign of x. Got it? So how to design an algorithm to obtain sign of x, how to design an algorithm to determine square root of any number. Got it? Got it? Clear? Such problems, okay, solving equations, system of equations, computing definite integrals, evaluating functions, and so on. So now look at the second point. The majority of mathematical problems can be solved only approximately. So what it means, approximation, okay? I meant to say, can anyone tell me the square root of 4? You'll clearly say is 2, exact. But what about the square root of 2? Square root of 2, we don't have an exact. It's an approximation. We may, after decimal point, we may round up to 2 digits. Or after decimal point, we may round up to 3 digits. Or after decimal point, we may round up to 4 digits. Okay. So I mean to say most of the mathematical problems are approximation. For example, square root, sine, they are approximation. Means we won't get an exact value, exact answer. We'll get an approximated answer. Okay. So that we call an approximation problem. So clear? So with this, we will finish. We have covered about the different types of problem types: sorting, searching, string processing, graph problems, combinatorial, geometric, numerical problems. With this, I'll wind up my session. Thank you.